Hello, everyone. So today it's my pleasure to introduce Rex Liu, who's a postdoc at Brown University in the lab of Michael Frank, and also working with Thomas Serre. And so I wanted to say something smart because Rex is a very smart guy. Uh, but basically, Rex did his PhD at Cambridge University, working on something that I have no clue what it is, but it's called discrete gravitational approaches to cosmology. And so I started looking at the PhD thesis and I said, like, I don't understand anything about this, so I'm not going to say anything about this. But I caught a quote in the beginning of the thesis that kind of reflects what Rex is about in science. And so the quote is a Confucius quote, and it goes like this: "The ancients, wishing to cultivate their persons, first rectified their hearts. Wishing to rectify their hearts, first sought to be sincere in their thoughts. Wishing to be sincere in their thoughts, first extended to the utmost their knowledge. Such extension of knowledge lay in the investigation of things." And so kind of this reflects of what Rex is he's a true researcher. He loves to think about stuff. He loves to communicate and collaborate and so on. So after doing this PhD in cosmology, he went on to thinking about the brain, which doesn't surprise me given this quote. And now he's working with Michael and Thomas Serre in this kind of trying to understand how the human brain does generalization. And the work that he's going to present us today is really about this kind of trade-off between expressivity and compositionality in this kind of notion of generalization, and specifically within reinforcement learning tasks. So Rex, thank you again for presenting in this seminar, and please take it away.
All right, thank you, Chris, for that very kind introduction. I'm really surprised you actually managed to find my PhD thesis. Thanks. All right, thank you all for having me here today. I'm going to talk about some work I've been doing with Michael here at Brown. So this is on the idea of how we can compositionally generalize across different task models to try to solve different tasks in reinforcement learning. Right. So as you probably know, artificial intelligence has made tremendous progress in recent years. In fact, they're now able to surpass even the best of us on a wide range of really challenging tasks. For instance, excuse me, there we go. They're able to beat the best players on a wide range of Atari video games. They're able to beat the best human players on complex real-time strategy games like StarCraft. And they're even able to beat the best world players in Go. This is regarded as one of the hardest board games in existence. To give you an idea of how hard this is, there are maybe about 10 to the 170 different board configurations in Go. But the number of atoms in the observable universe is only 10 to the 82, which is far smaller in comparison. So basically, it's impossible to learn and memorize all the board configurations. It's impossible to solve Go. But in spite of these really impressive feats by AI, there are ways that humans are still better than artificial agents. One important difference is that humans show a high degree of behavior flexibility, and they can readily transfer knowledge from one task to another. For instance, the same human can in principle play chess, cook a meal, wash dishes, converse in English or Latvian, drive a car, and so on. The best artificial agents we have seen so far, though, are all specialist agents. They've been trained to do just one task, and one task extremely well. Not only do these agents struggle when they have to solve multiple tasks, they even struggle to transfer knowledge between tasks that are meaningfully similar to each other in some way. So for example, let's consider the Atari game Breakout. If we train an agent really well to solve this version of the game, and we want asked to play a different version where we move the version on the right, where we move the paddle up slightly, the performance breaks down entirely. For humans, though, this is a very easy transfer problem. So if artificial agents are to effectively model and replicate our natural intelligence, this ability to transfer between tasks is one important problem it needs to solve. So to transfer between tasks, we need to be able to abstract out some latent knowledge that can be applied to other tasks. There's a lot of evidence in psychological and cognitive science literature that humans will try to infer the latent structure or the latent rules that govern a task. In reinforcement learning, we call these structures or rules the model of a task, and humans will try to transfer this model across different tasks. Models are important because they tell us what actions we can take and what happens when we take these actions. That is, they predict the consequences of these actions. So we can use these predictions to explore different possible courses of actions and try to plan the best one to take. For an example, if I know the rules of chess, I can use these rules to try to consider different possible moves several steps in the future to try to find the best move I want to take. But as I was saying before, though, humans will also try to transfer these models or latent task rules across different tasks. So for example, if someone knows how to drive in London, they should have no trouble driving in Tokyo, Hong Kong, or Delhi, because all cars drive on the left in these places. Likewise, if someone knows how to drive in Montreal, they should also have no trouble driving in Paris, New York, or Santiago, because cars drive on the right in these places. So in both cases, this ability to transfer relies on our ability to abstract out a set of latent driving rules from the specific city in which they apply. Also, if someone knows both sets of rules, they're able to switch between them quickly and infer which set they should apply when in a new city. So the big question is, how can we get artificial agents to similarly learn and transfer such models across different tasks? Well, models often have compositional structure to them. We can break a model down into at least two parts. The first is like the goal, what you want to do. For in this example, let's say we want to go and get ice cream. The second part is what we call the transition function. So how do you want to go about doing it? For example, in this case, you want to take the bike there. There are two ways we can transfer models, though. We can transfer entire models as a whole. That is, we can take specific combinations, specific pairings of goals and transitions, and transfer that as a unit. The other approach is we can try to transfer each component separately from each other. So we can try to transfer goals independently by itself, and we can try to transfer transitions separately from goals by itself. The literature shows that humans are known to adopt both strategies. So transferring model components separately is quite important because it allows for the possibility of what we call compositional generalization. What this means is that we can readily create new models by taking familiar components that we've seen in the past and recombine them in new ways. So for example, suppose we knew different modes of transportation, like riding a bike, driving a car, or riding a skateboard. And suppose we knew how to reach different destinations, like going to the bank or an ice cream parlor. Then we should be able to travel to the bank on a skateboard, this particular combination of bank with skateboard, even if we've never done it before. This ability to compositionally generalize, that is to recombine familiar model components in new ways, gives us a greater flexibility in solving a wider range of problems than would be possible if we only transformed entire models alone. So to study this ability to transfer models, we considered a set of tasks that had explicitly compositional structure. So here the agent had to navigate a series of gridworld rooms. Each room had two components. The first is a hit and go. Excuse me. The agent needs to know, the agent doesn't know where this hit and goal is, but so it must explore to find this goal. The second is a transition function that the agent, which is also hidden from the agent, and the agent has to learn. So the idea here is that the agent is presented with 8 possible actions. There are 8 keys in which it can press. The 4 of these keys will do nothing. These are the blank keys that you see on the right in the screen. The other 4 will move the agent. If the agent pushes any of the other 4 keys, they'll move the agent along the card time. How these 8 keys map onto the 4 different map onto the movements, and this will change as well. So the agent must learn this. and transfer this where appropriate. So the idea is we have the agent navigate a series of these compositional grid worlds in sequence. The idea is that it should leverage knowledge of goals and transitions from prior rooms to solve new rooms whenever appropriate. This room has a goal in the red location, and it has that transition function. It has nothing at all in common with the first room. So the goal is in a different place. The transition function is also different. Then it goes on to the third room. It could be that this goal is repeats from the first room. It's familiar. So the agent should, in this case, try to transfer its knowledge of the goal over. However, the transition function here, so it has to learn that again as well from scratch. Now it enters the fourth room. Here, it could be that the transition function repeats from the first room. So it should readily reuse that if it can. But the goal is new again, so it has to learn that from scratch. So with this setup, we can study how agents transfer models from old rooms to new rooms. We can see how it transfers entire models as well as individual components, goals, and transition functions. So now the question is, how can we get agents to flexibly solve new tasks using prior knowledge that they acquired in previous rooms? We're going to consider three possible strategies. The first is what's known as a joint clustering strategy. Here, the agent learns and transfers entire task structures as a whole. That is, they learn specific combinations of goals and transitions and will transfer that as a unit. But the problem with this approach is that it cannot compositionally generalize. This is a bit more akin to what standard RL agents do. They learn tasks as one monolithic entity. So they don't really recognize substructure to that to the task. The second approach is what's known as an independent clustering strategy. Here, the agent will try to learn and transfer goals and transition functions separately from each other. So by separating out goals and transition functions, it allows the agent to be able to compositionally generalize. This means that it can recombine familiar components into novel combinations it's never seen before. But the limitation of this approach is that it cannot reuse entire structures, and sometimes this could be a good thing, especially if structures repeat and if there are structures that are regular and repeat. The fun approach, which is really the approach that I developed with Michael, tries to get the best of both worlds. So in this case, it will learn components independently of each other, and this is necessary for supporting compositional generalization. But it will also learn about the different possible task structures and try to reuse them as well. So I'm going to start now with the joint clustering agent. This agent will try to, as I was saying before, this agent will try to infer the correct model to use for each new task it tries to solve. The way the inference works, if for those of you who are familiar with this, is that it's based on the Chinese restaurant process or a Dirichlet process. I won't go into this in too detail, but this is pretty much how the algorithm works. It's a clustering algorithm. So for an agent enters the first room, and it has to learn a model for that room. So that we have these circle that we see in the screen there. Now it enters the second room, and it needs to learn a model for that. That model could also be described by the first model, or it could maybe belong to a different model altogether. So we create a new cluster and we assign the task, the blue dot, to that model. Now suppose the agent enters a third task and needs to solve that. Let's say for this task, it figures out model one describes the same task. In this case, transfer takes place. It doesn't need to learn the model from scratch. It can just simply reuse what information is it knows already about model one that it learned in task one and transfer this to task three. So let's continue. We enter the fourth task. It might be described model one. It might be described in model two, or maybe it's a new model altogether. So we create a new model and assign this task to that model. And the idea is that the idea continues. We go to a new task, find the right model, a new task, find the right model, a new task, find the right model. So the strength of this joint clustering approach is that it can transfer entire task models whenever these recur. But the problem is that it cannot compositionally generalize. So it cannot reuse individual model components. This is especially problematic when it enters a new task. And it may see familiar components, but in new combination. So if it may enter a new task, it sees a familiar goal and a familiar transition function, but it's never seen this particular pairing of the goal and transition function before. In this case, it'll ignore everything it learned before and try to relearn everything from scratch. So a transfer fails in this setting. So just to summarize, the table, the joint agent can transfer structures, but it cannot transfer components. So now the idea then is to introduce an independent clustering agent that will cluster components separately from each other. And the idea is this will allow the agent to compositionally generalize. So to walk you through this, the agent enters the first task and it has to learn the goal for this task. And it assigns the task to the first goal model that it has. But it must also learn a separate transition function. And it assigns the same task to the transition function it's learned for this task. It now moves on to task 2. Let's say this task involves a completely new goal. So it has to learn a new goal function for this task and create a new cluster and assign the task to that goal cluster. But let's say the transition function repeats from task 1. Then the agent can simply reuse the transition function it learned in task 1, transfer that knowledge over rather than learn it from scratch. Let's now move on to the third task. So let's say in this case, the goal is familiar, it repeats from task 2, but the transition function is new. In this case, it could transfer goal information over, but the transition function has to be learned from scratch. Now let's move on to the fourth task. Here the goal is familiar. It's the first goal it saw, so it can transfer this knowledge over. And the transition function is also familiar. It appears in the second task, so it can also transfer this information over. But note that this pairing of goal 1 and transition 2 has never been seen before. So this is an instance of compositional generalization. So the advantage of the independent agent is that it can compositionally generalize. It can transfer components independently of each other. But the main shortcoming of this is that it cannot transfer entire structures. And as I was saying before, if the structures do repeat, this would be less optimal. You may sometimes have correlations between task components, and it would be helpful to be able to learn those correlations and leverage that to better inform your transfer. The independent agent ignores all higher order correlations between components, and it will be suboptimal when these correlations exist. So to give you an example of this, returning to our navigation example, there may be correlations, for instance, between where we want to go and what method of transportation we choose to get there. If we're going to travel to fun destinations, like we want to go to an ice cream park or to get ice cream, or we want to go to a fun fair, we may prefer to take more recreational fun modes of transportation. We may prefer to go we may prefer to bike there, or we may prefer to skateboard there. But if we're going to more business-like destinations instead, we may choose to drive instead. So there may be correlations, for example, between the mode of transportation we take and the destination we're going to go to. An agent that can recognize and exploit such correlations between task components will therefore be more optimal. So we introduce, therefore, a hierarchical clustering agent that tries to get the best of both worlds. So it will learn and cluster model components independently of each other, like the independent agent, and this will allow it to compositionally generalize. This will allow it to reuse components across different tasks in new ways. But it will also learn these higher order structures that combine the components together. And it will learn models of how these components should be combined together. The inference of these model components proceeds in a hierarchical manner. So first off, we learn a set of clusters of room clusters that describe different possible models for these tasks, different possible models of task structures. We also learn a set of clusters that will we also learned subclusters for describing goals and transition functions. But we learn them separately from each other. And the separation again allows us to recombine familiar components in new ways. But then the room clusters have to learn how these components should be combined together to form different structures. So specifically, the room clusters will learn how we take components from the goal clusters and transition functions and combine them in new ways within their own models. So specifically, the room models define conditional probability distributions over different possible goals and transition functions. And this idea is that model components that the model components that are learned outside the room clusters can be shared across different models. We may have the same goal, for instance, in red appearing across different room models, and we may also have the same transition function appearing across different room models. So I'm going to stop here briefly just to make sure that people, if you have any questions, I'm at this stage, I'm happy to follow that before I move on to describing the tasks. So do people have any questions at this stage? Okay.
I think it's pretty clear, so you can continue.
Okay, great. Okay, great. Thanks. Okay, then, great. Okay, as I was saying, the idea is that the hierarchical agents can transfer both components and structures, and we are interested in knowing how these different agents will perform across a range of different tasks. So we designed a few tasks to test the relative transferability of these different agents. The first learning environment consists of a set of rooms using 2 goals and 2 transition functions. And we've set this up so that each different possible pairing of goal and transition function appears. So we have a total of 4 different rooms. This learning environment is more optimal for the independent agent. And if you look at the set of results here, what we showed, we have each of these agents visit each of the rooms 4 times in random order. So that's the x-axis here is showing you the number of which visitation of each room, which visitation of the rooms it's seeing. This is average across all the rooms. And the y-axis shows the number of steps on average it needed to take to solve a room. So this first data point here shows the number of steps each of these agents needed on average to solve a room when seeing it for the first time, the second time, third time, and fourth time. The key point, though, is the first data point, because that shows how well are these different agents transferring. We also simulated another agent, which is given in the black line here. We call that the flat agent for reasons of literature. I won't get into that, but the key idea is that this serves the baseline because the flat agent does not transfer. Whenever it enters a new room for the first time, it'll learn everything from scratch. So this sort of tells us what agent that does not transfer, how well it does. And we can compare that against that as a baseline. So the idea here is that the lower the number of steps taken, the better. But I think this graph here, I think the inset on the top right is a bit more informative. So this shows you the fractional improvement of each of the agents against the flat agent baseline. And what we see is that the independent agent performs the best. The hierarchical agent is also doing pretty well in this case. So it's showing that even though this is optimal for the independent agent, the hierarchical agent still does a decent job. And we see that the joint agent does badly altogether. For the second task, we designed a learning environment where the joint agent would be favored more. So in this case, we have 4 goals, 4 transition functions, but each goal is paired with only 1 transition function. So there's a 1-to-1 relationship between that. We had a total of 8 different rooms. So each pairing of a goal and transition is represented by 2 different rooms. And the idea is that if it visits 1 pair for the first time, it should be able to transfer, the joint agent should be able to transfer knowledge of that model to the second room that also shares that pairing. So in this case, we see if you look at the inset in the top right, we see that the joint agent performs the best, but it's also the hierarchical agent performs well here too. And the independent agent is doing the worst. So the key thing we noted across the last two slides is that only the hierarchical agent performs best in both the independent and the joint environments. Otherwise, the independent agent does better in one but badly in the other, and vice versa for the joint agent. So this suggests that the hierarchical agent is more adaptive overall. Now we're going to move on to two sets of tasks where neither the joint nor the independent agent should be doing well. These tasks should only favor the hierarchical agent. So this is a task with more mixed statistics. The idea is that we have a set of rooms that can be regarded as purely joint. Rooms 1, 2, 3 are all belong to one particular pairing of transitions and goals. So these are a set of joint rooms sharing one particular model. Rooms 4 to 6 share another pairing and are also another set of joint rooms. And the remaining of the rooms have independent statistics between the transitions and the goals. And if we look at the graphs on the right again, we find that for the joint room, okay, it makes sense the joint agent's doing the best. Hierarchical agent's doing pretty well though. In the middle graph, in the middle inset, these are independent rooms. We see the independent agents doing really well, joint agents doing badly, and the hierarchical agent's still doing quite well. But if we look at the performance across all rooms at the bottom inset, we see that the hierarchical agent does the best overall. So the hierarchical agent is the most adaptive, and it can perform well across a wide range of different task contexts. Finally, this is just another environment. This is an environment where rooms have conditionally independent statistics. So if you look at rooms 1 through 8, these are rooms where the transitions and the goals are independent of each other within this cluster. Rooms 9 to 16 have another set of another cluster where the transitions and goals are also independent of each other. But the independence is conditional, basically. If you know you're in one if you know you're in one cluster of rooms, then you know that the possible transition and goals are if you know that cluster, then you know that the possible transitions and goals should be constrained. So if you're in rooms 1 to 8, you should not be looking at the last two. You should not be looking at the blue or yellow goals, or nor should you be looking at the bottom 4 transitions. Similarly, for the other cluster, if you're in the other cluster, you should not be looking at the green or red goals, and you should not be looking at the top 4 transition functions. We find the independent agent won't be able to do this, even though this environment has independent statistics. The independent agent will look at all the different transitions and all the different goals, so it will be less adaptive in this case. And if we look at the inset of results, we find that across all rooms, the hierarchical agent is still doing the best. It's outperforming the independent agent. So to give you an interim summary, we find basically that the hierarchical agent is the most adaptive across all the different environments we have considered. But so far, the tasks we considered are fairly simple. So what happens when you scale these up to more tasks with more complex structures? So here we've considered a far more complex task with a hierarchical structure to it. There are many parts involved in this task. So the agent must solve a sequence of rooms in what we're calling a castle. Each room consists of an upper level. Sorry, I apologize for the inability to point my mouse. So I'll try to explain it verbally. But if you look at like the box on the left, you can see that as a room. That room has an upper level, which is the level on top you see, and it has 3 sublevels, which are noted by the colored patches on the bottom. You can think of these as dungeons as well, and it's a bit inspired by video games like Super Mario Brothers or Zelda, where the hero can go into different sublevels as well as come out and go to the main level. So the idea is that in the upper level, the agent must navigate. The upper level has a set of 4 different doors. I've shown that. The upper level has a set of 4 different doors, and each sublevel has a set of 4 different goals. That's shown in that grid world at the bottom there. Each of these grid worlds also has their own transition function, which is shown on the right. So the idea is that the agent will first start in the first room in the upper level. The agent must then navigate to the correct first door in its upper level. That door, when it enters that door, it'll take the agent down to the first sublevel. In that sublevel, it must find which of the four goals is the correct exit, take that exit, and go back to the upper level. Then it moves on to the next door. It enters that door, goes into the second sublevel, finds the correct exit, comes back up again, moves on to the third door, finds the correct, enters that door, enters the sublevel, solves that sublevel, comes back up, then it moves on to the fourth door. That fourth door takes the agent to the next room. So that's what the pink arrows are showing. That's showing an exit to the next room. The problem is that so there are several issues with this. We made this task especially hard. The agent has to find the correct, it has to go to the right door in the right order. It can't jump ahead to the wrong door. It can't try to even exit to the next sublevel. The thing is, if it makes a mistake, it's sent back to the beginning of the first room. Similarly, in the sublevels, we make it really hard. If the agent makes a mistake, if it goes to the wrong goal, it's sent back to the beginning of the whole task. This makes mistakes really, really costly, and this will strongly favor agents that can transfer prior knowledge from prior rooms effectively. Yes. So this sort of task structure affords a high degree of transfer possible. The idea is we can transfer, for instance, transition functions across different layers of hierarchy or across different rooms. We could also transfer goals across different layers of task hierarchy and across different rooms. So there's a high degree of transfer possible here. Now, so when we go to like these really complex, more complex tasks, the thing to keep in mind is that the number of possible structures will explode combinatorially. This makes like the brute memorization approach that a joint agent adopts two structures really bad. For one thing, this strategy would have very, very poor memory complexity because of the combinatorial explosion. You're going to run out of memory very, very quickly. Moreover, most structures will unlikely repeat in exactly the same way within an agent's lifetime. If you see one particular complex structure with a very, very specific combination of goals and transitions or whatnot of a particular configuration of components, it's unless that structure were really important, it's highly unlikely you're going to see it in exactly the same way again in the future. You may see different parts changed out. You may see like parts are similar, but then parts may also be different. So memorizing exact structures is really, really bad. Instead, what's more likely to happen is that you're going to see substructure motifs that will repeat. And it would be better to learn and transfer those instead. So we ran our different agents on a series of different tasks. We did not do the joint agent in this case for the reasons I just gave. The joint is just a bit bad versions of this task. In the first version, the task had mixed statistics between the different model components. And as we see, the hierarchical agent is doing better in this case. So that's a bar graph on the left. We also ran a version of this task where we tried to make the components of the task as independent as possible. What's really interesting, though, is that the hierarchical agent is still doing better in this case. So there's still some residual structure that the hierarchical agent is learning and exploiting here. So if the hierarchical agent is solving these tasks more quickly, that means it must be transferring goal information more quickly. This allows it to be able to predict the correct goal more frequently on its first attempt. So we looked at basically how frequently the different agents were finding the correct goal on their first attempt at it. We find that there is no difference for sub-level goals, but we see that there is a difference between the agents for the upper level doors. So the hierarchical agent is actually doing a better job predicting the upper level doors when it's trying to find the correct door on its first attempt. So we broke this up further. We looked at each of the four doors individually, and we see that a difference emerges from door 2 onwards. The hierarchical agent is predicting the correct door from door 2 onwards. And so the question is, why is this? Why is it that what is allowing the hierarchical agent to, what knowledge is there that lets the hierarchical agent predict what the correct door is from door 2 onwards? Well, if you look at it turns out that the hierarchical agent is actually sequence is finite. Not all door sequences will be represented. So the sequences will provide some residual structure that the agent can learn and exploit and transfer over. So it could be that your dictionary of different transitions in the upper level and door sequences corresponds to what you see in the table on the left. Some rooms may have the transition A paired with door sequence 1, 3, 4, 2. Others may have A with 2, 3, 4, 1, and so forth. But the thing is, across all the rooms, you have these. Let's say we only had these 6 transition functions C. It knows right away what the whole door sequence is. It knows right away the door sequence should be 2, 1, 4, 3, because there's only one sequence that is paired with the transition C. But if it goes to another room and it sees transition A, it needs a bit more information. It may need, maybe it sees that the first door is door 1 that it needs to get to. Based on that, then it can figure out the rest of the sequence is 3, 4, 2. That's the first row there. That's because there's only one door sequence. There's only one sequence that starts with transition A and door 1. It could be that if you see door 3, A3, then you need more information. You need another door before you can resolve the whole sequence. But this regularity lets you predict what the future. This regularity lets you predict what future possible doors are. It narrows down the possibility based on what you've seen before. And on the graph, and we can actually quantify this by looking at by measuring the Shannon information that partial door sequences give. We find in the graph in the partial sequence we've seen so far that the probability that the hierarchical agent will be better at guessing the door compared to the independent agent, that's a y-axis, increases. So that's what we're seeing in the graph on the right. So the main idea here is that the agent learns, transfers, and exploits knowledge about door sequences. This is a form of substructure in the model and leverages that to improve its performance in guessing doors. So this sort of brings me to the end of my talk. I'll just summarize quickly. So humans are the overall takeaway is that humans are in general more adept than machines at transferring knowledge between different tasks. One of the key ways that humans do this is that they are able to learn about latent task structures and use this to support transfer. And humans are known to transfer structures both compositionally and as a whole. We've introduced an artificial hierarchical agent that can do this as well. Our agent is more expressive and it transfers knowledge. It transfers knowledge about both components as well as entire structures effectively across a wider range of environments compared to alternative transfer approaches. And in more complex tasks, we find that it learns and transfers substructures rather effectively and not just entire structures. So if you want to learn more about this work, we do have a recent paper out. It's been published in Artificial Intelligence, and the reference and link is I've shown down below. So thank you all very much for your attention. I just want to thank my lab here at Brown very much for their support, and in particular, I want to thank Chris. Who I want to thank my PI who is in the back in the middle, as well as Chris who's beside him, for inviting me. Thank you all very much for your attention.
Thanks, Rex.
Thanks.
So I guess we have plenty of time for a round of questions, either here or on the chat. Okay. Yeah, después del chat primero acá y... okay.
All right, Doctor. So you gave this example of all the capabilities of reinforcement learning models have with like
Yes.
playing games of like StarCraft and beating the top players of the world and that kind of things.
Yep.
And what came to my mind is, do you have like an idea of where is like the other border of the current status of what generalization can you make in the reinforcement that you give through these hierarchical like architectures to your models? Like, do you know, for example, in the game StarCraft, would
Yes.
your model be better at learning playing a new race
I
than
see.
a,
Okay, I guess like for one limitation is I guess more of a technical one. We still have one challenge right now is trying to get to implement this. So like okay, StarCraft have these really impressive agents. They all rely on deep neural networks to do. We haven't quite been able to translate this yet into that domain. So that's I guess maybe the first step. That does require like either having a really efficient memory to keep track of what tasks you've seen in the past. That may be possible with like things like neural Turing machines, differential neural computers, but we have not yet quite explored that. So I guess that's one maybe limitation. In terms of capability, the other limitation is that our framework does require that you know like you're in a new task, a new context. It may also be that you're like the context changes are a bit more subtle, so that would be another like I guess obstacle we would have to overcome with this approach. So
all right.
okay, does that
Okay, thank
yeah, I'm
you.
not sure. Yeah, okay, thanks.
Another question? Maybe the chat question?
Sure.
Oh
I
yeah,
see someone has their hand raised, and I'm not so I hid my controls, but I can't. So I'm not trying to bring them back. So
Mircea, dale Roma. You can ask the question.
Okay, so I'm sorry for the background noise if there is too hard. So I wanted to ask, in order to compare this learning approach across problems at the theoretical level, I am curious how to two questions. So first question is how to measure the depth of the, say, under inverted commas, the underlying tree that measures the hierarchicity of the task. So how can I distinguish a deeper versus a shallower tree or measure this depth? And then of course, if the hierarchicity of the learning model, is there a deeper hierarchicity that you can imagine for deeper tasks?
I see. So you're asking basically about how we determine the hierarchy of the models.
Of the models and of the learning model and of the problem to solve, of the task to solve.
I see.
How
So
to measure that?
Okay. Okay. So hold on. Let me see. Let me just make sure I understood you correctly. So for instance, like here we sort of have two levels of hierarchy, right? We have like the parental clusters, which I'm not sure if you're familiar with hierarchical Dirichlet processes, but the idea is that the goal clusters at the top is like the parental cluster, and and we also have a Dirichlet process, a CRP, a Chinese restaurant process within each of the different room clusters, and it's in a hierarchical relationship. So
okay.
So, I mean,
so I agree. So here there are two levels of hierarchy in a way,
right.
inside your brain.
Yes, that's right. That's right. So you're asking
how yeah. If this has to match the hierarchy of the task, hierarchicity of the task, or is it, or how do the two match? How can I?
Yeah. Okay. So yes, it does have to match it. At this stage, what we sort of coded so it matches the hierarchy of the task. All it's inferring or learning right now is like what are the different structures within this particular hierarchy. So we know that there are going to be the hierarchy consists of the hierarchy consists in this case of just two parts, goals and transitions. When we go to more complex tasks, there may be more parts, so we'll have to actually change the hierarchy. Right now we're hard coding that. So that's also another limitation.
Okay, so like you could, in theory, you could have a more complicated learning model in which this is the two-step case, and then there is the general n-step case for that would be adapted to to thinking ahead in several different moves.
Oh,
How
I see.
can I
Oh, sorry, you're
connect it?
referring to the planning problem. Oh, okay. We're not actually okay. So planning problem, we were.
I mean, no. I'm just imagining how would be the three level learning model instead of two. Yeah, that, I don't know.
I'm not. I think what you're talking about sounds like planning, because you're talking about, if I were to think about like 2 steps ahead, 3 steps ahead, 4 steps ahead, like in chess, for example. That is.
I mean, this is so. No. That was just a newcomer remark. I'm just. I'm curious. How would be the 3-level version of this learning model instead of Oxford?
Okay. So this is okay. Okay. So in reinforcement learning, so I was mentioning that in reinforcement learning, we have models of task, and the idea is we use these models to plan actions. This is actually learning the model. We're not talking about how we use these models to plan actions. That part I actually didn't go into in my talk. There are many ways you could do that. You could do tree search, and that would consider it would use these models, and it would consider different actions like multiple steps ahead. But to do that sort of planning, you need to have these models to begin with. And the whole idea behind this problem is, how can we know what the right model is when we're in a new task? Once we have that model, then we consider what happens if we take 1 step into the future in this task. What happens if we take 10 steps in the future in this task? So that's sort of an orthogonal problem altogether. The way I've done that, if you want to know, the way I've done that planning is through a reinforcement learning algorithm called DINA. This is something that is like, it's an old algorithm in Sutton Bardo. It's nothing too fancy, but that's the approach I've taken for the planning side. But the planning is independent from learning what the right model is to begin with, so that you can do the planning. I'm not. Does that answer your question? Or
I think Rex and Mircea,
yes. So thank you.
Maybe can I jump?
sure.
Just to clarify, maybe Mircea's question. So the transition clusters, like the transition functions, they incorporate the 2 levels of your diabolic grid rules, right? I mean, they have actions from the first and the second level, right?
Okay. So, I did not, sorry, I don't have the slide for that, but the model for that, as I said, as I was saying before, that does involve different hierarchies. So we actually were using a different model for that. It's not, I only showed the model for the simplified grid world, but in that case, the room clusters will keep track of transitions for the upper level. It'll have a CRP for transitions for the upper level. It'll have a CRP for transitions for the sub level. It'll also have CRPs for door sequences and CRPs for sub-level goals. So it sort of does inference for the different model components. It's actually the model for that is a bit different. It's a bit more complex. I mean, that is one limitation, that each time we go to a new task with a different hierarchy, we do have to change and hard code different parts of this. But then once we know what type of structure we want, or the space structures we want, then we can do inference within that space to find the correct model according to the correct task.
Cool.
Okay.
Anybody else? I actually have one question.
Yep.
Maybe kind of a devil's advocate type of comment.
Okay, sure.
So I was wondering whether you think us as humans, we actually do implement something like the hierarchical clustering. So we are more like a hierarchical clustering agent, or are we something like at the start a hierarchical clustering agent that decides to become joint or decides to become independent, given more information regarding how the world is structured, basically?
I see. Well, I would argue that the hierarchical clustering agent subsumes both the joint or independent agent, because you can, in principle, have so I didn't really get into this, but the room clusters that you see here, for instance, they are quite expressive. You can have, I said that these models define conditional distributions over goals and transitions. You could, and each of these distributions is implemented with a CRP, a Chinese restaurant process. So you can have some room clusters where you only have one goal and one transition. That would give you a joint structure, and you can have maybe multiples of those. So the hierarchical clustering agent captures the possibility of learning purely joint structures. The other possibility is that you have one room where you put everything, all goals and all transitions you've seen inside there. That would give you effectively both extremes in its space. It does that, and it does more than that. So I'm not
Cool.
sure if that's okay.
And then maybe I have maybe two last questions.
Yeah.
The first one is like a clarification question on the last part. So is it that
Okay.
the hierarchical model is performing some type of, kind of deductive reasoning as it discovers that the state space crunches or gets smaller because it has already seen a bunch of sequences, and then it can directly just say,
Oh.
okay, like C has to be associated with this sequence because I've seen the other ones or something like that. And is that what you like basically are quantifying with the Shannon information?
That's pretty much it. So I mean, in practice, basically, it will like look at the dictionary of sequences it's already seen before, and it will try to like from there infer what's the I guess it'll try to infer what's the best sequence, what's the best store based on the sequences seen before. So it will see, all right, I'm seeing transition C and I'm seeing transition 2. So from everything I've seen before, there's only one case that matches this. So I'll try that as my first guess. And if I'm right, great, I move on to the next door. If I'm wrong, that means I have to update and expand my dictionary now. So it could be that it could be, for instance, let's take the first sequence, like let's say transition A 1 3 4 2. It could be that the other A's exist, but it hasn't seen that before. It goes to the one room, it sees A1. By luck, it goes to another room, it sees A1 again. By luck, then it'll transfer. It'll just using seeing only A, it'll guess then the first word is 1, it'll be lucky and it guessed right, but that's pure fluke. So it's sort of learning and updating its dictionary as it goes along in the sequence. It's using prior knowledge transfer, which sometimes is favorable and sometimes it will mess up and give you negative answer. Okay.
Cool. Yeah. And then the last 100, not million, $1 billion question. So how does a neural network do this?
Artificial or natural?
Oh, artificial.
$1 billion question. Okay, I mean, first of all, Michael does have work showing that like the basal, his artificial neural network of the basal ganglia can mimic CRP like inference. Okay, so it's not like perfect, but it's mimicking, and you can sort of like imagine combining these in a hierarchical manner to try to model the different CRPs within your model. So that's one approach. But if you want to go to like deep nets, that is a harder problem, and that's something I've been thinking about. To me, I think you to do the CRP, you need to have a memory that keeps track of what tasks you've seen in the past and what model those tasks have been assigned to it. So you need a memory for that. The only memory I think of that is expressed enough to do this is probably something like the neural-Turing machine or the differential neural computer. That's my best guess. I have not tried it myself, but I'm thinking that might be the way to try to mimic this.
We should think about this together.
Yeah,
because we've been thinking about it in that way as well, actually.
Okay.
Yeah.
Well, yeah, I'd have to be happy to talk more with you about this if that's something of interest to you.
Yeah. Okay, so I guess thanks again, Rex. And yeah, we'll keep on speaking. I don't know if you see me now.
No, I don't see. I hear you, but I don't see. Okay, I see. Okay, I see. Yeah.
All right. Thanks again, Rex. Thank you.
Okay, thanks. Thank you again, Chris, for reminding me, and thanks for setting this up.
Yeah. Thank you. Bye-bye.
Bye.